nuts and bolts of kind of how our sun works. And again, a lot of this is stuff that, I don't know if you jotted down, if you took notes during the video we watched on Monday. But our sun is beautiful, and we're going to talk about it in terms of kind of being a typical star. It's about halfway through its life cycle at this stage, and so it's got about another 5 billion years to kind of basically do what it's doing now. It's done it for 5 billion, it's got another 5 billion as in a B left. Along those lines, when we think about here on Earth how we heat things up, one way is we take a log and we burn the log, okay? Now, if you only have a limited amount of energy you can get from that log when you burn it. So if the mass of the sun, we know about how much the sun weighs because of Newton's laws of motion. If you take the mass of the sun, and if you were to completely burn it, which would be hard to burn it out there because there's no oxygen, but anyway, if you were to combust it, it would only last for about 10,000 years. And I kind of put a timetable of it's been 5 billion, and it's got another 5 billion at this stage of its life. So that's not it. Another way, and actually this is how it got so hot in the first place. Remember, you guys on your last exam told me kind of how our solar system came to be, the whole solar nebula theory, okay? So anytime you take matter like the solar nebula and you bring it in from being out there to being in here, you're actually converting potential energy, less potential energy, more kinetic energy, and so more kinetic energy, more heat. Okay, so that is one way to heat things up. But based upon the mass we're talking about, instead of B with a 5 billion years, or actually 10 billion years, it would only last 25 million years. So, of course, I'm leading you up to the way that our sun is powered is the same way that stars are powered, and that's nuclear fusion. Nuclear fusion. And I'm going to, who came up with E equals mc squared? Einstein, yep. I'm no Einstein, but E is equal to mc squared. And actually, in the crux of that little simple equation is why nuclear fusion gives us so much energy. We'll talk about that here in a minute. But I mentioned 5 billion and 5 billion. We're kind of halfway through it using up the hydrogen, basically, to convert it into helium, and it's going to run out in another 5 billion years. But I put that here. So one of the things about all stars, including our sun, is that only, stars are hot, right? they are. They're hot on the surface. They're hot on the outside. The video kind of talked about how the atmosphere of the sun is hotter than the surface of the sun. Isn't that weird? But only in the core is it the hottest temperature for nuclear, bless you, for nuclear fusion to happen. You got the high temperatures and the high pressures. So this is kind of showing you nuclear fusion. Now we talked about atoms and what's at the center, what particles are in the, well, it starts with the letter N. What do we call that middle of an atom? A nucleus, very good. And in the nucleus, what two particles are there? Protons and neutrons, exactly. Very good. Protons and neutrons in the nucleus of an atom. These little pictures I have up here from, actually this is from, say Canvas. This is from your OpenStax. Anytime you see this kind of here, this is from your OpenStax. By the way, I think Friday maybe, I'm going to actually do a quiz, and it's not going to be a hard quiz. And I kind of want your feedback. Is anybody using your OpenStax book? I kind of want some feedback. So, not that you have to, because it's kind of set up where you almost don't have to. But it's a pretty good textbook and available. So Friday there will be a quiz. All right, so yes, you guys told me protons and neutrons in the nucleus of an atom. I mention that because these figures from OpenStax are only talking about the nuclei. What else? What is outside the nucleus? Electrons. No electrons here. So with nuclear fusion, basically you're taking the nuclei, cramming them together to make a heavier nuclei. This could be hydrogen going to form, what's the He stand for? Helium. Helium, yeah, it could be, but it's a little more complicated than that. We actually have a second type of nuclear reaction, which is fission. So fusion put together, fission, break apart. Like I think cells, when they do their division, they call that cellular fission, maybe. I don't know. But fission, breaking apart. A good example of this, you probably heard uranium sometimes is a good fuel for nuclear reactions. And uranium has a big old honking nucleus. So this is the nucleus. The two colors are the protons and the neutrons. And here you see the nucleus of the atom breaking apart and forming two smaller atoms. The electrons just kind of go where they need to go. So this is fusion and fission, too many F's. So I want to talk a little bit more about nuclear fusion, okay? This is a near miss. Can you kind of see that? This could be like a hydrogen nucleus, which is just a proton. This could be a hydrogen nucleus, and they come near each other, and it's a near miss. There's no fusion going on there. Your best odds of getting fusion, I think the video talked about this, is you're having a lot of energy, high temperatures, and having them pretty close together, high pressures. High temperatures, high pressures in the cores of stars get the conditions so they can actually collide and form a heavier nucleus. Okay. Now here in a minute, I'm going to show you, once this happens, well, that's all well and good. Where's the energy? And I'll kind of try to talk you through that. But this is no fusion. This is fusion with high temperatures and high pressures. So up here, these P's stand for what? Okay. Protons. Yep. And N stands for neutrons. Very good. And you told me HE stands for helium. Perfect. So now on your test, I'm going to have to kind of figure out now how much do I really want them to know. And I'll try to kind of on the review sheet how much you know about nuclear fusion. But honestly, it's not as simple as hydrogen plus hydrogen goes together to form helium. It's a little more complicated. And it looks something like this. So we have hydrogen, we have 4 hydrogens going to form this kind of funky looking, this is just kind of like what we call deuterium, heavy hydrogen. Now, I don't know if you can see this, but we have, during the collision, oh, it's kind of small, but we have a couple of little particles coming out. I'm going to show you what those particles are in a minute. Then these two things actually pick up another hydrogen proton, and they form this kind of intermediate thing. This cool thing, do we talk about, what are gamma rays? What would you tell somebody is gamma ray? Shortest of waves. It's high energy electromagnetic radiation. Perfect. Exactly. So this little squiggle, that's what's going to heat the Earth. Okay? So then we're not quite done because we don't quite have helium. These guys come together. Okay? And notice when they come together, you have 2 hydrogens or 2 protons that are kicked back, and you end up with this thing's called a helium. This finally is a helium. The most common form of helium has 2 protons and 2 neutrons. It's mass number 4, because mass numbers we take the protons plus the neutrons. Yep, so that's helium. This kind of shows, actually, this shows the overall, where we have 4 protons coming together to make this one center of a helium atom. So the squiggles were gamma rays. The little particles you see right there coming out are the neutrinos and the positrons. We're going to talk more about neutrino, or we could talk more about neutrinos. I can't remember if I left it in here or not. So E is equal to mc squared. Energy, according to Einstein, is equal to mc squared. What is c?
Speed of light.
It is the speed of light. And what is m?
Yes.
It is mass. So here's the deal. In this process, gamma rays, that's your E. In this process, that's your energy being released. Okay? And I'm here to tell you, if you weigh these 4 protons, if you compare that to the weight of this thing, you lost mass. How much mass? About 0.7%. that is the mass that is gone or converted into energy. That's kind of how that works. I think it's pretty exciting. That, in a nutshell, is what's going on in the core of our sun and in all stars. Well, we're going to talk more about stars. And stars that are in their what we call main sequence, they're kind of their first stage. That's what they're doing. More complicated stars, more massive stars are doing something even more sophisticated than this. So I finally just this afternoon, this morning, I guess, went out and found this little cartoon. It's amazing what you can find online. But if you read it, this husband and wife are familiar with the sun losing its mass, 0.7%. Okay, a lot. What did I say? 600 million tons of hydrogen is converted, and it's losing. So you take 7% of that. Oh yeah. Okay. So that it's losing what? 4 tons. That seem right? If you take 600 minus 596, you get 4 tons each second. So it's losing 4 tons each second. It's a lot. So anyway, yes, we have the wife anxiously looking out at the sun, and the husband says, after reading that the sun loses 600 million tons every second. I don't think that jives with this. It would be 4. Do you know what I'm saying? I'm thinking 4. Aren't you? Because it still has the mass. It's just no longer hydrogen. It's helium. I think the cartoon is wrong. I'd go with my slides. But it's taking hydrogen and making helium, so it still has matter, but now it's not hydrogen, it's helium. Okay. So I'm going with 4. So you take this and go 4 million tons every second. Is it still there? Yes, it's still there. How does it look? The same. Anyway, I just thought that was funny. This kind of does the same. This is the same figure. And to summarize things, I would say you take 4 protons in. What you get out, you get a helium nucleus, 2 gamma rays, 2 positrons, 2 neutrinos. That's it. And a partridge in a pear tree. Yep. And you lost some mass. If you weigh, we sometimes call them the reactants and the products. If you weigh the 2, they're not going to weigh the same. This is going to be lighter. And that's the mass that is converted into energy. So sometimes if you have your slides here, you can put a little star there. This is probably the slide I'll refer to if I'm kind of looking for something, question to put on your test about fusion. But I'll try to let you know when that time comes. All right. So do these particles, what do you think? How many people think that they look like solid particles? How many people think they look like gas particles? I think they look like gas particles. They're just zooming around. What happens if we take gas particles and keep them up with their zooming? They zoom faster or slower? They zoom faster, exactly. Okay, so I think that this is kind of what I'm trying to say here. So you zoom them fast enough, and it's possible they could run into each other and overcome the resistance for fusion and actually fuse together. But what really helps in that too is if we increase the density, increase the pressure too. So temperature and pressure. Cool. Well, our sun, I've been kind of talking about, I'll go ahead and put it on a slide, or I'll grab my pen. How long did I say we've got for our sun to continue hydrogen fusion? Yep, another 5 billion years. After 5 billion years, our sun will no longer be at what we call hydrostatic equilibrium. And we're gonna, I like this unit of material because we're gonna talk about what stars are doing. Stars, in addition to our sun, what they're doing. And they're not all at hydrostatic equilibrium. So we have the pressure of gravity pulling in, just like this diagram says. Gravity would go like this, pull matter of the sun in towards the core of the sun, but kind of the energy that's being creating in the core actually has an outward pressure. So, we've talked about forces. You have an intuition of forces. If you have 2 forces and one's greater than the other, then one's going to win out. So if gravity was stronger than our pressure going out, our sun would shrink. Okay, if the pressure going out was greater than gravity, our sun would swell. Okay, and the fact that it's neither shrinking nor swelling means that those two forces are in what we call equilibrium. They're equal in magnitude and opposite in direction. So hydrostatic equilibrium is going to be for another 5 billion years or so. I need to talk a little bit like the video did about the layers of the sun. And actually I've got a little video to show you this layer of the sun. I didn't talk much about it, about this idea of convection, but you ever heard that hot air rises? Yeah, and it does because those particles are going faster, just like you told me. They are occupying more area, so then that means that it's less dense. If it's fluffy, less dense than its colder surroundings, it's going to go up. So that's one leg of what we call convection currents. So it goes up, okay, cools down. As it cools down, it will sink. In this case, at the sun, we have the source of the sun heating it up. We kind of have these convection cells. If you've done much with plate tectonics and kind of the Earth's crust, that's what's happening in the mantle of the Earth too. So let's see about this. All sorts of places. If you're boiling a pan of water, do you have, like, the water near the bottom of the pan is going to get warmer than the water up here. So if you kind of watch, sometimes you can kind of see swirls come up. The blob of hot water comes up and warm, cooler water will fall down. So this is the outermost. This right here, convection zone, that's the outermost layer of the interior of the sun. Outermost of the interior. Outermost layer of the inside of the sun. Okay. Those squiggles are the same squiggles we saw a minute ago. Those squiggles, think of them as the gamma ray energy. Okay. That's coming from nuclear fusion. So what happens after nuclear fusion is the energy is released and the energy finds a particle. Which particle do we only come to? The energy finds a particle, imparts that energy to that particle. Now that particle picks up energy and it's going to go faster, right? That one can collide with this one, lose some of its energy, make this one go faster. Okay? And so in that case, this guy goes faster. It can go randomly hit this one. Okay? It slows down. It imparted its energy to this one. Did it impart all of its energy? Not necessarily, yeah. But it's kind of like it's a kiss here and a kiss there, and we all pick up energy along the way. The video, and I've got a number to go along with it, but do you guys remember on the video that there was something that lady talked about how long it takes energy that's created in the sun's core to get from the core outward? It's like thousands of years. So this is called the random walk. And this is what happens in what we call the radiative zone in the sun's center. So random walk. Of course, that's the sun. Energy is created here, and you can kind of see those little passing energy from particle to particle. The caption says anywhere from 100,000 years to 1 million years. Are you serious? Yes. So it makes you just want to go out and spread and look at the sun and say, thank you for that energy. Neutrinos. Where did we see neutrinos a minute ago?
In the out.
In the out, yes, in the out, exactly. So one of the things, being scientists and being as y'all are, inquisitive, you might be like, okay, if the sun is doing what I just described in the out, we should actually be seeing the positrons and the neutrino particles, right? And as it works, what this is trying to show you is the neutrinos don't do any random walk. The neutrinos, once they're created during nuclear fusion, they're out of there. Okay, neutrinos. The thing about neutrinos, and actually that's kind of why they don't have to do random walk, is neutrinos are a type of particle that don't interact with other particles. So that's why they just pretend like the sun's matter is not there. That's actually why neutrinos, and scientists have made, if you Google neutrinos, scientists have specifically looked for neutrinos on Earth. Because if that's coming from the sun, then those neutrinos must be hitting the Earth in large numbers. And they've had, I think, better success than they did 10 years ago when I first started teaching this class. Okay, so neutrinos go right out. Okay, so core. So here's the 3 layers, and I have a slide kind of showing them here in a minute. But your core is the first one. That's the center. Radiative zone is beyond the core. That's where the random walk occurs. Convection zone, that's definitely not as slow as the radiative zone. The convection zone was what we saw with the lava lamp. Kind of the last little bit that the energy needs to go from the hot radiative zone up, okay, and it travels using like plasma, okay, and then it cools down and comes back down, heats up. Okay, so that's the last little bit of getting energy out. Okay, cool. This actually is kind of a complicated little slide. I like the video. Do you remember, and it's called the SOHO. I just think that is a neat name. SOHO. Anytime somebody talks about the SOHO, they're actually talking about an observatory that is in orbit about the Earth. I think it's in orbit about the Earth. I have to double check. We've actually got satellites. Remember the video talked about that stereo, which at the time I don't think it was entirely online. But that, I think, goes in front of the Earth, orbiting the sun. Isn't that cool? Anyway, I digress. So in order to study the sun, a lot of times you have to block out the sun itself to kind of study the sun's atmosphere. I guess I should say study the sun's atmosphere. So this is like eclipsing the sun. This right here is a different image of kind of showing you, I think it's maybe an infrared from a different imaging device for the sun. Okay, you heard him talk about solar wind. I almost wanted to giggle. I heard on the video last night, or yesterday, 2 days ago. So solar wind, right, happened when the sun began fusing hydrogen in its core. Okay, the solar wind. What else do we have about the solar wind? The solar wind makes this big kind of bubble into outer space, okay, called the heliosphere. And I've heard it described, and I think it kind of alludes it to on this slide, that the heliosphere is actually a protection for our solar system from kind of bugs, for like I'm talking science fiction here, but bugs sort of wandering in. They have to be going upstream of our positive pressure that our sun's creating. And I think I mentioned the other day that, was it back in the 70s, that NASA launched 2 missions, Voyager 1 and Voyager 2, and actually they are leaving the heliosphere. Okay, they're actually still sending back information. Just think that is amazing too. And then actually, as they leave the heliosphere, we would call them interstellar probes, because they're actually between stars, our sun and the next star, interstellar. I think that's a movie, isn't it? So, all right. So back to the layers of the sun. Talked about solar wind. Okay. So now the atmosphere of the sun has 3 layers. And I liked what that video talked about. I mean, I talked about this, the atmosphere of the sun kind of leaving with the corona. These are listed from outermost to innermost. So if I'm kind of going, core, radiative zone, a convective zone, then I probably would go photosphere. I'm going to put 1 here because it's closest to the convective zone. I'm going to put 2 here for chromosphere, and 3, the corona is the outermost. Okay. What I started to say is, and I hadn't thought about this before, but it's kind of like the planets are in the Earth's, not Earth's, the planets are like in the sun's atmosphere. If we're in the heliosphere, if I listened to that video right, I just thought that was it. But notice this is consistent with what the video said, that the corona is the hottest layer of the sun's atmosphere. Now, you might have heard this past August with a solar eclipse, and I've heard a lot of great stories. It was kind of cloudy where we were, but during totality, the moon goes in front of the sun's disk, and you can see the corona. I did see some cool pictures, but I think that is so cool. Okay. When you glance at the sun, and you should never really look at the sun, but if you look at the disk of the sun, you are actually looking at what we call the photosphere. To me, photosphere is kind of the beginning of the surface of the sun, which of course there's no rocky surface to stand on. But we kind of consider the photosphere is the last layer of its atmosphere. I think it's the surface. Okay, and then these three down here that we talked about before. So I'm going to put core as 1. Radiative or radiation zone is 2. That's where the random walk occurs. And then 3, the convection. So on one slide, actually, I've got both the inner, and then I've got what's called the outer, or the atmosphere. Cool. So the photosphere is, if you glance at the sun, the photosphere then is what you're seeing. And the reason you're seeing the photosphere, like this says, is that the corona and the chromosphere are transparent. You can't see them unless it's a total eclipse. This temperature actually was a temperature we saw a while back on a black body radiation curve. Remember where we had wavelength down here and intensity here? And we had a curve that was about 6,000. What does K stand for? Kelvin. Yeah, it's about 6,000 Kelvin. And actually, this brings up a good point. When we talk about other stars and we talk about their surface temperatures, we're talking about the temperature of their photosphere. So we're looking at the photosphere here, and I'm not sure if I've really, I guess maybe I've noticed this, but if you look towards the center of the sun, it looks brighter, and the edge of the sun looks kind of dimmer. I guess this is having photographs, because you never look at the sun. Okay, and that dimness is actually called limb darkening, and it has to do with you just basically have less little energy transports out there, so it is literally a little dimmer. Okay, so I have a video to show you here in a minute, but this is a close-up of the photosphere. And if we look down each of those little holes are called granules. And if we were to look down those little holes, we would see convection happening. So can you see this convection here? So we're looking down into the convection zone. So let's take a look at this little video. Yeah, right? That was odd. Okay, so this is again showing you the granules would be these circles up here, although were they all the same size? And then it falls down along the edges. What's the difference between this top one and this bottom one? Sunspots, yes. So, does the sun always have sunspots? Does the sun always have granules? Sometimes that's a test question. Does the sun always have solar wind? The sun always has solar wind, always has granules. So yeah, there's a close-up of the granules, which is not really clear, and this is a close-up of a sunspot. Did you hear the video on Monday? Are sunspots usually alone? Seems like he kind of talked about a lot of times they're in pairs. If they're in pairs, they can lead to other things. But actually, sometimes they are alone. So that's kind of. This right here. So which of these, recognize these words? Photosphere, chromosphere, and corona. Which one's the hottest?
Well,
corona. My corona. Yep. And what this is showing you along the y-axis is temperature, and this is distance from the sun. And so I'm actually going to show you something, and I hope it's going to ring some bells. And since I've been teaching this, I guess for 15 years instead of 10, but they've come more into understanding why the corona is so darn hot. And I think on the video we watched, it talked about kind of this idea where actually energy is liberated from the photosphere out into the corona by these, I think you might have called them filaments, I'm not sure. But anyway, I have a video to show you these spicules. Now, spicules are on the surface of the photosphere in the chromosphere, if I think I got that right. And they're very dynamic too. So let's take a quick look.